Close enough. I will I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. Lord, I thank you for the students. And I just pray you bless this class today, Lord. In your name I pray. Amen. Well, I think there's something obligatory I have to say today. If you liked convocation today, you might be a redneck. I mean, come on. Obviously. No? Okay. You talked about Rwanda. When I you talked about Rwanda the whole time? Okay. All right. I guess I missed lecture 13. By my count, 13. This is on section 2.6, which is concerning cosets and Lagrange's theorem. So let me get right to it. Definition. All right. If H is a subgroup of G and A is an element of G, then Ha is the so-called right coset of H. This is the set of elements HA such that H is an H. And A is likewise AH such that H is an H. Yeah. Yes. Sorry, it's awful. I will cease and desist eventually. This is the right. It's the right H coset generated by A. This one here is the left H coset generated by A. Oh, I forgot. There's a subsidiary quote I should probably mention to you today, and this seems relevant. Is that, and this is a quote that's dear to me. I am not left-handed, and this seems relevant to me because Nicholson uses right cosets, which goes against the grain for me. Like I'm a left coset kind of guy, but I guess he's not left-handed. I don't know. He does everything with right cosets, which is fine. I mean, you can use one or the other. But and so I will follow Nicholson and use right cosets. But if you look at stuff from last year, you'll find left cosets by and large. Okay? So let's look at some examples. Example 1. If I have G equal to the cyclic group of order 6, say generated by A, I can take subgroup H generated by A cubed, right? So the subgroup is 1 and then A cubed, whereas of course C6 is 1A, A squared, A cubed, A to the 4th, A to the 5th. There you go. And we can look at the cosets, right? So, for example, 1H is actually equal to H1. That's just H again. If we do A times H, it's also equal to H times A because this is a commutative group. And so, in fact, that's A comma A to the 4th. A squared H is HA squared. And that's A squared A to the 5th. Again, the left and right cosets are automatically equal here because we're in an abelian group, right? So left-right multiplication, hard to tell the difference. Example 2, the quaternion 8 group. So we're going to look at the quaternion 8 group with, you guys remember the quaternion 8 group? I don't know. Example 2, Q8, which would be you know, plus or minus 1, plus or minus I, plus or minus j, plus or minus k. It's got 8 things in it, right? And I'll look at the subgroup generated by I. Okay? Subgroup generated by I, it's a group of order 4. It's got 1, I, minus 1, and minus I in it. Right? And so you can look at cosets of H. I'll say, here it matters, right? Hj and jh might not be the same. I think they actually are the same here, but that's kind of a fortunate thing. If we take hj, the right coset generated by j, that's going to give us j, ij, minus j, minus ij. So I'm just multiplying each element in the subgroup by the representative, generating this coset, j in this case. And then you know the rules for quaternions. We can simplify this. This is equal to j, k, minus j is already simple. And what's minus ij? That's minus k. Right. You can likewise, and I'll leave this as an exercise for you guys, but it's not hard to show that in fact this is equal to hk, and it's equal to h minus j, and it's equal to h minus k. If I look at any of these right cosets, they're all hj. They're all the same set. So what I'm trying to tell you is that hj is h coset generated by either j or k or minus j or minus k. You have 4 choices. Anything in the coset will generate that coset. Notice when I talk about coset generation, it's not the same as subgroup generation, right? It's not the cyclic. It's a different notion of generation. Example 3. We can look at S3, which I would encourage you guys to learn to think of as sigma tau, such that sigma cubed is epsilon, tau squared is epsilon, and sigma tau sigma is equal to tau again. So this is a generators relations version of the symmetric group on 3 symbols. And so we could look at H, right, equal to, let's say, the subgroup generated by sigma. So that's 1 sigma, sigma squared. What are the right cosets of this one? So let's see here. We can look at H tau, yeah? And what's that going to be? Tau, sigma tau, right? And sigma squared tau. Now, of course, we can also use the generators to rewrite this. This is the same as tau, tau sigma squared, tau sigma. And so it's then fairly, well, I don't know if it's fairly obvious, but it is in fact also true that h tau is equal to h of sigma tau, and it's equal to h of sigma squared tau. You can calculate those just the same. You get the same 3 elements. There are 2 cosets here. One is the subgroup H, and the other one is h tau. Or you could say h sigma tau. Or you could say h sigma squared tau. These are all the same right coset. In contrast, I think this is a good example to do this while we're at it. Tau h, what's that equal to? Well, we got tau sigma squared, right? Oh, this is embarrassing. I mean, it's not embarrassing, it's just not especially exciting. It just so happens that the left and right cosets of H are equal. I mean, tau H is equal to H tau in this case. On the other hand, if we look at K equal to the subgroup generated by tau, which would be what? Oh, I'm sorry. This one is supposed to be an epsilon, right? Okay. So subgroup generated by tau would just be epsilon tau. And I can look at the right cosets of this. K sigma, sigma, tau sigma. I can look at K sigma squared, which is sigma squared tau sigma squared. Right? Of course, well, anyway, so there's that. In contrast, we could look at sigma k. What would that be? Okay, let's see here. This is, sorry, that's awful. Sigma tau. What is sigma tau? Sigma tau is tau sigma squared. So you can see that the right coset generated by sigma is not equal to the left coset generated by sigma for this subgroup. Just because it happens for one subgroup doesn't mean it's going to happen for all. Okay, anyway, so these are, I just want to give you some concrete calculations of cosets before I start telling you theorems. All right. One of the things you might notice in all of our examples so far, I got two more examples, is that the union of the cosets is the whole group, right? Do you see that? Example 4, we could look at G being the integers, and we can look at the subgroup being 4 multiples of the integers. In this case, we have additive cosets, so we've got like h plus 0, which is just 4z. We have h plus 1, which we would denote as 4z plus 1. We have h plus 2, which is 4z plus 3. We have h plus 3, which is 4z plus 3. I'm sorry, what happened to me? That was a 2. There, fixed. Anyway, all of these, the notation is this. 4z plus j is defined to be 4k plus j such that k is an integer, and this is for j equals to 0, 1, 2, and 3. So these are the right cosets of the subgroup 4z, which you get, I guess, 4 tuples if you like. I think the cool thing here to notice is that if we take 4z and we union with 4z plus 1, and we union with 4z plus 2, and we union with 4z plus 3, what do we get? No, we did not get 4z. We get z. See, because these 4 cosets partition the integers into disjoint subsets. These are cells of a partition of the integers, right? Where 2 integers are equivalent, the equivalence which affords this partition is the equivalence which says that the 2 integers are equivalent if their difference is a multiple of 4. That's equivalence relation. Example 5 I like. Here we have G being the non-zero complex numbers under multiplication, and H the circle group, which we denoted C0. You could call these the unimodular complex numbers. Basically, they're e to the I theta, such that theta is a real number. So if we look at right cosets, so let's let Z be in C star, and we can look at the polar form of Z. Z is the modulus of Z times, say, e to the I theta naught, right? Where theta naught's standard angle. Pick your favorite argument, if you know what that means. So then Hz would be e to the I theta modulus of Z times e to the I theta naught, such that theta is a real number, which you can simplify. Modulus of Z times e to the I theta plus theta naught, such that theta is a real number. And so geometrically, it's clear what this is. This is a circle of radius modulus of Z. And so here I can picture the cosets. They're concentric circles around the origin. The origin's not in there, of course. I tried, because this is the multiplicative complex group, right? But this is a typical, right, coset. They're circles centered around the origin of the complex plane. All right. This is a good set of examples to get us started. Hopefully I have not spent too long doing that. Okay, good. So you'll remember the definition, I think. So theorem 1 of 2.6. We again have H, a subgroup of G, and A and B elements of G. All right. Then we have this list of demands. H is equal to H1. 2. Ha is equal to H if and only if A is an element of H. 3. HA is equal to HB if and only if A, B inverse is an element of H. 4, if A is an element of HB, then HA equals to HB. 5, either the cosets are identical, HA equals HB, or they're disjoint. And 6, last but not least, the distinct right cosets of H are cells of a partition of G. All right, let us prove these things. I brought markers that work today. I don't know where they went. So number 1, this is, you'd like this for homework, right? So check it out. H is equal to H such that H is an H, right? Which is equal to H times 1 such that H is an H, right? Which is, by definition, H1. Yay, done. 2, we'll use 3 to prove. 3. So let's assume that HA is equal to HB, right? So what's that mean? No, it does not mean that. Since 1 is an element, and we have to think about points. So since 1 is an element of H, which is a subgroup, right? This implies that 1 times A, excuse me, like I said, the left cosets. So 1 times A, okay, we're fine, equals to A is an element of HA, right? But this is equal to HB, right? So just to emphasize, thus, A is an element of HB, okay? Hence, there exists, let's say, H1 in H, such that what? A is equal to H1 times B. consequently, solve for H1. H1 is equal to A, B inverse. And this is an element of H. That completes the forward implication, right? Now let's go the other way. Assume that A, B inverse is an element of H. What's our goal? We would like to show that HA is equal to HB, right? So if AB inverse is an element of H, thus there exists, let's say, H2 in H such that A, B inverse is equal to H2. Okay? And then I'm trying to show these two sets are equal. How do I do that? How do you show sets are equal? You pick a point in one, and you try to show it's in the other, right? That shows one subset. So, there are various ways, but let X be an element of Ha, right? Thus, there exists H3 in H such that what? X is equal to H3 times A. Then what? How can I convert that A to a B? But A, B inverse equals to H2 implies what? A is equal to H2B. Thus, X is equal to H3 times H2B. And as H3 comma H2 in H implies that H3 H2 is in H, we find X is an element of HB. But X is an arbitrary point, therefore HA is a subset of HB. At this point, Nicholson says similarly the other direction, but that's kind of true, but it's kind of not here because A and B are not quite symmetric in their role in the theorem. So I'm a little bit disappointed in his lack of detail here. So let me give you the detail. Let Y be an element of HB. Then there exists H4 in H such that Y is equal to H4 times B. What do I need? I need to convert that B to A, right? I can do that if I go back to how do I solve this thing for B? I'll put a parenthetical remark here. So we know AB inverse equals to H2, right? So that implies that B inverse is equal to A inverse H2, which implies that B is equal to A inverse H2 inverse, also known as B is equal to H2 inverse A, right? I'm sure some of you could have derived that easier. That's just what occurs to me at the moment, okay? And I didn't want to look at I have something else in my notes, but whatever. So B we can replace with B we replace with what? H4 H2 inverse A. And as H4 H2 inverse is an element of H, we find Y is an element of HA. Therefore, HB is a subset of HA. Hence, HBA is equal to HB. That completes the proof of 4. I'm sorry, 3. I wanted to go through it in all of the details because these are details that I expect you can replicate for yourself. Okay, so let's see here. Then how do you, I said that we could get 2 with 3. How does that go? Would you guys see it? Let b equals to 1, right? I'll put it here. We set b equals to 1. So we have HA equal to H1 if and only if what? Using 3. A 1 inverse is an element of H, right? So this is a horrible way of writing A as an H, right? So there you go, that's 2. 2 is easy once we have 3. How do we prove 4? Let's see here. So if A is an element of HB, right, then what? Then there exists H in H such that what? A is equal to HB, hence H is equal to AB inverse is an element of H, therefore HA is equal to HB by 3. Right? So I like Nicholson's argument. I can chase points for number 5, but it's kind of nice to use his argument. You guys will like his argument. So either HA is equal to HB or HA intersect HB is empty set. So what should we do to prove this? Suppose, I mean, if HA intersect HB is the empty set, great, true, right? So what else is there? HA intersect HB is not empty, right? Therefore what? X is an element of HA intersect HB, right? Thus, X is an element of HA, right? And X is an element of HB. But what else is X an element of? Think about 2. Right? X is an element of what? X is an element of HX, right? And what did we have before? So we get what? By 4, right? Wait a minute. I forget which one I'm using. I'm an idiot. Well, anyway. Thus, HA. These things get to be so close to me in my mind, I have a trouble separating them at some point in the proof, because these are all kind of very much related. But you guys tell me, what argument am I using to say HB, HA equals to HX, and HB equal to HX? How is that present from what I have here? We're using number 4. Let's see here. A is an element.
X is an element of HA.
Right. So by 4 then. But then you see what happens here. This and this, of course, are the same, right? So therefore, HA is equal to HB. So that proves 5. Either the right cosets are the same or they're mutually disjoint. And then 6 follows from this. See, because what 5 essentially says is that, well, it says that if we say the right cosets are cells of a partition, right? They're disjoint. Then we have that from 5. What else do we need for it to be a partition? We need what? Right. So the only gap then is if A is an element of G, then A is an element of HA, right? So every element in the group is contained in a right coset. So there you go. It's a partition. In fact, this is the partition which is afforded what equivalence relation? Like what equivalence relation takes right cosets as its partition? What is the equivalence rate? Two elements in the group are equivalent if what? You gave me a formula. Very good. If you're like, he's like A and B are equivalent if A, B inverse is an H. Great. Another way you could say that would be A and B are equivalent if they generate the same right coset. Okay. Lemma. Let H be a subgroup of G. All right. Then 1, the cardinality of H is equal to the cardinality of HA is equal to the cardinality of AH, and that's true for all A and G. Again, cardinality. So that means it could be, we're using that, it could be infinite, right? The map HA maps to A inverse H from right cosets to the set of, from the set of right cosets to the set of left cosets is a bijection. Or if you like, a one-to-one correspondence. There's one thing I missed, guys. If we were working with left cosets instead of right cosets, almost the same proofs go through, right? But there is a big difference. AH is equal to BH if and only if what? Yeah, B inverse A is an H, right? I got very confused last year when I failed to recognize I was trying to prove this with that condition. I think I put that on their test. That messed with their heads pretty good, and mine too. So don't do that. It's easy enough to remember, right? You can kind of like symbolically derive it. If you just multiply both sides by B inverse on the left, see what you get? You get B inverse AH is equal to H. I mean, that's formal nonsense, but it does also help you remember the right rule. Yes, we could also. This is the inverse of that, so it's a subgroup, yeah. Okay, so the proof here of 1 is essentially just that if we look at psi of H equal to HA, and if we look at, let's say, phi of H equal to AH, these are both bijections. And so they prove that those being bijections proves that the cardinality of those different sets are the same. And then for 2, well, we have what? HA equals to HB if and only if what? A B inverse is an element of H, right? Which is, uh-oh. Sam. Is it that late? No. Curses. All right. How do I convert this to a left coset condition? How about this? This is A inverse times B inverse, right, is an element of H, which means that A inverse H is equal to B inverse H. So what that says is if you send the right coset HA to the left coset A inverse H, it's a bijection because of this equivalence. I will not belabor this. That brings us to the concept of an index. What's an index? The index of H in G is the number of cosets, possibly infinite, of H in G. So, for example, the index of H here would be what? Here, there were two cosets, H and tau H. For K, so we'd have that the, let's see here, S3 H, sorry, no brackets, is equal to 2. This one, we have S3, the index of K is 3. Okay? So that's index. Notice that in example 4, what's the index in example 4? The index is 4, right? So even though every coset is infinite, right, it chops it up into just 4 pieces. What's the index of H in example 5? That one's infinite, yeah. There's infinitely many. So that would be an example of a subgroup of infinite index. So here's Lagrange's theorem. Let H be any subgroup of a finite group G. Then we get two things. Number one, the order of H must divide the order of the group G. But more than that, the quotient order of G divided by order of the subgroup is in fact equal to the index. It's easy to see that in all of the examples I've given you today, except for the one where you can't count. The one example that doesn't count is example 5. I mean, literally, anyway. How do you prove this? This is one of my favorite proofs in the whole course. It's simple. It's really, really simple. So what you do, you got a finite subgroup, right? So a finite group. G is finite. I can't spell. G is finite. Therefore, let HA1, HA2, HAK be distinct H cosets of G, right? By definition, K is equal to what? It's equal to the index of G by H, right? Because that's the number of right cosets, which I'm saying there are K of them. Why does there have to be a finite number? Right. Right. If there was an infinite number of cosets that were distinct, that would mean there's an infinite number of points. But that's impossible for our finite. Right. Great. So then notice that G is equal to HA1. Well, I mean, I guess I don't have to say. Sorry, I'm just lost my place. Excuse me. By theorem 1. What was theorem 1? HA1 union HA2 union union HA3 HAK. So I'm using what? I guess I'm technically using an extrapolation of 6, right? Well, no, 6 actually was this, right? The distinct right cosets of H are cells of a partition of G. So that means the union of the distinct right cosets give you back all of G, right? But then we can count, right? What's the order of G? It's the sum, I equals 1 to k, of the order of H a sub I, right? But what did the lemma say? It said that the order of every right coset is the same as the order of H, right? So I can simplify this sum. That's just the sum, I equals 1 to k, of the order of H, which is a silly finite sum, right? That's just k times H. Thus, the order of G divided by the order of H is equal to k, which of course was just the notation I invented for the index for this proof. And there you go. That's Lagrange's theorem. We had this result before for cyclic groups, but now we have it for finite groups. At this point, I get to share with you some exciting corollaries. All right? Corollary 1. If G is a finite group and G is an element in G, then the order of the element divides the order of the group. How do we prove this? How do we prove the order of the element divides the order of the group? Ah, the cyclic group generated by the element. Very good. So corollary 1 simply says that if the order of G is less than infinity, then the order of G divides the order of G for all G and G. Too many G's. Oh well, it's too late. I should really use X or something for the, here. Is this better? X. X. See, there you go. Proof is just what King said. If we have from our work on cyclic groups that the order of the cyclic group subgroup generated by X is equal to the order of X, right? And of course, the cyclic subgroup of generated by X is a subgroup, right? Therefore, by Lagrange, we have that the order of the element must divide the order of the group. Corollary 2. If G is a group and the order of G is n, then G to the n equals to 1 for all G and G. What's the proof? If the order of G is equal to m, then what? That's equal to the, yeah, so by corollary 1, that implies that m divides n by corollary 1, right? Hence what? N is equal to what? N is equal to Km for some K and Z, which implies then that G to the N is equal to G to the M to the K, otherwise known as 1 to the K, otherwise known as 1. Okay, so this is great. If we know the order of the group, you take any element of the group, raise it to that power, it's the identity. Inescapable. These are not too impressive to me. I mean, they're cool, but they're not too impressive. This right here makes me go, what? Corollary 3, this is neat. If P is prime, all right, then every group of order P is cyclic. In fact, G is equal to, is generated by G for any G not equal to 1 in G for such a group of prime order. How do we prove that? Yeah.
Well, the subgroup has to have an order of 1. That's the only number, because everything in the group will be relative to prime to the order.
Mm-hmm. Okay, so let's go with that. Let's say that G is not equal to 1 and H is equal to the subgroup generated by G. So then your point is that the order of H, right, has to divide P, which implies what? Either the order of H is equal to 1 or the order of H is equal to P. So then what? Can the order of H be 1? Right, but 1 and G are elements of H, right? So therefore H is not equal to the trivial subgroup. Hence, the order of H is equal to P, which is equal to the order of G. So by the usual finite set theory, H must be G. But that means that G is generated by G. But the G we picked was arbitrary, non-identity element, right? So that shows that any non-identity element generates the group. And that's corollary 3. there are 3 like equally exciting things past this point that I can't get to because my time is up. But so I'll have to stop here today. But this is fascinating, right? Because we have seen groups of prime order do what? They've all been cyclic, haven't they? Right? But there's a few other really, really non-obvious things that he proves from this. I'll wrap that up next time. So let me give you back your test.